Thank you very much, and happy to be here. My name is Davide Lombardi from Xi'an Jiaotong-Liverpool University, or ex-JTLU, and I'm here to present the paper entitled Defining a Blockchain Verified Specimen Passport for 3D Standardization. The paper has been primarily written by Giancarlo who is a PhD student in our university, and co-authored by me and Theodoros, that it's here with us too. I think we are all pretty much familiar with concrete as a material and concrete structure and concrete applications in architecture, as well as I think we all know a bit about what 3D printing is, and in some respect also 3D concrete printing. Now, we asked ourselves a question at a certain stage when Giancarlo started his PhD, why 3DCP is not getting used or massively deployed. Yes, we have examples of 3D printed structures. We know a lot of, or we have seen a lot of pavilion temporary structure, but why is not a standard or an industry standard? At the end of the day, we are still building with beams and columns, I would say 99.5% of what we see around us. Well, we recognized a few issues. First of all, limited adoption of rigid standards, critical traceability and assurance gap, inadequacy of conventional concrete paradigms, which means basically we are lacking in standardization. In other words, if we go and ask for building permission, most likely the office of our hometowns will not recognize how to build a structure in 3D concrete printing because they don't have the standard. Okay? So we can rely, of course, on 120 years of experience on concrete regarding common standard objects, again, beams and columns, but how about a 3D printed concrete? We have anisotropy of the material, we have layers, so we have an whole set of different problems. Of course, the current standards that we have, which are built on the knowledge that we acquired over this century, basically, are primarily prescriptive standards. The current quality assurance system lacks a tamper-proof end-to-end linkage. Here we go why then blockchain will come into place at a certain stage. And again, the traditional standards ignore the variabilities like interlayer adhesion, which is not existing in traditional construction, and print path dependency. In other words, what is new, what happens as a new part in the 3D printing component is not considered into the current regulations. We set up 3 research objectives. So the research gap, the absence of a shared validated standardization framework for 3DCP, a broader research aim, which is to generate a flexible performance-based standardization paradigm. So this is the final goal of the study as a whole, and the specific paper objective for today, which is the foundational data scheme and operational logic for 3DCP, specimen passport. Of course, we went through a step of data definition. So we asked ourselves what constitutes a comprehensive, immutable data record for this kind of technology application. We looked into blockchain automation, asking how can smart contracts and decentralized ledger technology can be utilized to automate the verification of a production data, and how can we integrate those 2 aspects into a regulatory framework. As we said, we looked into the standardization paradigm. We didn't find much, yet we found something, for example, the ISO 8015, as well as an initial kind of, not framework, but how-to manual that has been developed in Germany. We looked into application of blockchain in construction, and of course, as we know, since we are all here, blockchain technology offer a few features like immutability, transparency, and cryptographic security, which is absolutely needed in the case of validation of a specimen for structural utilization. The embedding material passport and circular economy concepts, which are of course also at the foundation of any kind of research nowadays in AEC and operation industry. And last but not least, also quality control. 3D printing concrete is, if you wish, even a much more alive material than simply 3D printed. There are further parameters to take into consideration, as I already said, like, for example, the interlayer. So the quality control of the production is absolutely a must. Methodology. We split the methodology into a number of steps, of course, starting from data acquisition, of course, also in our case, relying on sensors, material specifications, environmental monitoring. We have been working in a confined environment, so in a kind of factory, if you wish, scenario, which is the Fab Lab, our Fab Lab in the design school of XJTLU, envisioning a scenario in which components are pre-built or pre-printed, if you wish, in this factory and then shipped out in the building site. Processing and logging, so validation, synchronization, hashing the data for efficient and secure blockchain storage. And here with a bit more detailed, where we also run into the layer number 3, which is again the blockchain layer, where we utilize a permissionless blockchain network with a hybrid on-chain, off-chain storage strategy. Of course, the size of the files plays a role. What can be taken into the blockchain stays in the blockchain. What is way too heavy, IPFS or similar kind of technologies. And the layer number 4, which is the application layer, where we provide, and we aim to provide, an interface for stakeholders to actually apply such approach. In fact, one of the main limitations often regarding innovation in our sector is the difficulty, if you wish, in the user interface or in understanding what is happening at each stage of the process. We created an experimental setup, also thanks to the support of the civil engineering department in XJTLU. We characterized first the material initially through 80 specimen cases in a robotic workshop, effectively implementing and validating the framework data acquisition layer for real-world additive manufacturing workflows. As I said, we are working in a factory-like environment, in a safe space with 3D print, ensuring the same level of humidity, temperature throughout the whole production, and then the specimens are shipped to the other side of the campus, so not that far, into the civil engineering lab for cracking and getting the data of the resistance of the material. We, of course, maintain identity and traceability, so including a unique production package ID that contains raw material certificate and verifiable hash, as well as the G code for the production and reproduction of the test. Performance grading system, so we assigned a standard grade, like could be, for example, M20, based on the compression test. Of course, as I said, we don't have standards for 3DPC, so we had to start from something, and we said, okay, let's start from 20 megapascal, or we start from 25 megapascal of resistance. So we start from what we already know, and we are start building now the new standards, if you wish. Process and performance data, integrating real-time in-process sensor reading and final mechanical performance test result to document the build journey and material behavior. And last but not least, digital integrity, of course, and certification. We defined a smart contract architecture, let's say divided into 3 steps. As we said, there is a production passport NFT, which creates unique transferable digital identity of the specific specimen for each production run with a versioning system. A validation registry contract, which establishes a multi-validation consensus mechanism mirroring the scientific peer review process. This is also something that came from our previous studies on how to build consensus around a specific validation process. And data provenance contract, so in order to maintain a comprehensive chain of custody, tracking material from the sourcing to the final testing and then off to the building site. And on the right, you can see the overall workflow that you find, of course, also in the paper for more details. What are the results? Well, we've tried to achieve a scientifically rational approach to design choices, so NFT identity in order to mitigate the risk of counterfeit or duplicated batch records, a multi-validation consensus approach in order to eliminate the single point of trust, which is a vulnerability in the system, somehow also, as presented in the previous paper, it's better to work when there are multiple, let's say, eyes checking the validity of the data, granular provenance tracking, so closest traceability gaps inherent in the layer-wise production failures by logging every material and every process parameter at a micro level. This is also a bit opening up to a spin-off of the research which will look also the composition of the material of the concrete per se, down to the production of the ink and the chemical structure of the ink that we are using. Hybrid IPFS blockchain storage. This is mostly for, let's say, a logistic-wise approach in order to simplify the life of those that are working with the different kind of files, and versioning system so that we can reconcile also tension between iterative research, improvement, and regulatory compliance by preserving a complete time-stamped history. What are we getting here? Well, a paradigm shift in quality assurance. Basically, we are moving towards the direction where the specimen passport can reorient our focus from the rigid perspective, rigid prescriptive process that we have now, which are based, as I said, in our knowledge of concrete structure, towards a more verifiable performance outcome, fostering innovation within compliance, so not just pushing something because it's new. We can do 3D printing with a KUKA, yes, but let's make it in a way in which also regulatory body can recognize what we do and the quality and the safety of what we do, of course, when we talk about architectural structures. And last but not least, enabling a responsive regulatory environment, following again the tragedy, for example, of the bridge in Italy, also in this case, ensuring that there is full trust from the stakeholders to the regulatory body, to the clients, is absolutely a must nowadays. Conclusion and future work. Well, the core conclusion is that 3D PC Specimen Passport is a critical enabler for responsible 3D concrete printing adoption, not anymore production. We know how to do it, but it's about the adoption. And of course, delivers essential traceability and auditability of our specimens. Current limitations that we are, of course, working on: manual input, which we try to reduce as much as possible, manual input of data. Industry alignment. This is something that we hope to break as soon as possible in order to make our technology available. And I have to say, China in this case could be the good ground where to innovate, also from an industry perspective, and interoperability. So try to move away from the gaps that exist while integrating BIM and LIMS workflows. Future work, technical development, so deploy at the layer 2 scaling, and industry integration, as I already mentioned, is a must in order to go beyond the specimens, which at the moment are still, let's say, cubes, 3D printed cubes, and going to something a bit more complex. Thank you very much.